All right, welcome back everyone to the deep dive. We're diving into something pretty huge today. We're going to trace the evolution of AI and IT since 2020. I mean, it feels like dog years in the tech world these days, so many big changes. It's easy to feel like you're constantly playing catch up. But with this deep dive, we're going to equip you with the essential knowledge to understand these really complex shifts without getting lost in the technical jungle.
Exactly. The landscape of artificial intelligence has undergone such a rapid transformation. It's almost hard to believe. We're going to break it down starting with where AI was before 2020. Then we'll explore the emergence of transformer networks, which are kind of the bedrock of many of the incredible advances we see today,
Mm-hmm.
like BERT, GPT, other large language models, which we'll get into,
Mm-hmm.
and things like multimodal systems, retrieval-augmented generation, Gen AI, and even AI agents. We'll unpack all of that to reveal just how much has changed and where AI is headed.
So before 2020, before all this transformative stuff, what were the main machine learning models being used?
Well, back then, the emphasis was on supervised and unsupervised learning. With supervised learning, models basically learn from labeled data. So you're feeding them data where the answer is known, and they figure out how to predict those answers for new data. So algorithms like linear regression and logistic regression were widely used for prediction and classification tasks. Things like deciding if a customer is likely to buy a product based on their past behavior.
Right, makes sense. And what about decision trees?
Yeah, those were important too. They help create those hierarchical branching decision-making models. They're kind of like flowcharts for AI and support vector machines or SVMs as well as naive Bayes. Those were common methods for doing probabilistic classification. So figuring out the probability of something belonging to a certain category based on its features.
Okay. So we had these tools for learning from labeled data. What about when you didn't have labels? What did unsupervised learning look like?
Right, so for data without labels, you had techniques like k-means clustering, which identifies natural groupings in data. Like if you had a bunch of customer data, it could cluster them into groups with similar buying habits. And principal component analysis, or PCA, was useful for simplifying really complex data sets by reducing their dimensions while still capturing most of the important information. But yeah, overall, these models were effective, but often for pretty specific problems. They weren't very good at handling more complex real-world scenarios.
I see. So AI back then was more like a collection of specialized tools for specific jobs. And how about neural networks? Were those being used much?
Oh yeah, early neural networks were definitely on the scene. Convolutional neural networks, or CNNs, they were showing a lot of promise in image processing, things like image recognition.
Mhm.
And recurrent neural networks, or RNNs, were the go-to for anything involving sequences like text or time series data.
So it sounds like they were making some headway, but were there any big hurdles with these early neural networks?
Definitely. Especially with RNNs, they struggled with what we call vanishing and exploding gradients. Essentially, this meant they had trouble effectively learning long-range dependencies in sequences. They had a hard time remembering information from earlier parts of a sequence, which is kind of crucial for understanding things like the meaning of a whole sentence or paragraph.
Oh, so it's like they had a short attention span when it came to text.
Yeah, kind of. And because of that, consistently achieving human-level performance on more complex tasks, those were really hard to come by. Getting them to work as well as you can was not really happening yet. And, another thing to consider is that the widespread adoption of deep learning within the business world, that was really just starting out.
Right. It wasn't quite mainstream yet, so it sounds like AI was still in its early stages back then. And getting these AI models to work well was that fairly straightforward.
Not really. Especially with those statistical machine learning models, there was a lot of manual effort involved in something called feature engineering. This is where domain experts had to really dig into the data, figure out what features were most important, and then handcraft them so that the models could learn effectively. And while deep learning was starting to automate some of that feature extraction process, it still required huge amounts of data, tons of data, and a lot of computing power, resources that weren't as readily available or as widely deployed as they are today.
So, kind of a resource intensive process, it sounds like. Okay, so we have a good picture of the machine learning landscape pre 2020. Now, let's talk about natural language processing, or NLP. How were computers understanding and processing human language back then?
Yeah, so in NLP, there are a few key approaches being used. One of the earlier ones was symbolic NLP. It was all about manually creating rules and using linguistic knowledge. Like, think of it as trying to teach a computer to understand language by giving it a giant dictionary. and a set of grammar rules.
Sounds pretty tedious. Did it work very well?
Not really. It struggled with the complexity of human language. Like, there are just so many nuances and variations in how we use language. It made symbolic NLP really difficult to scale to handle all those possibilities.
I see. So it was kind of a brute force approach that wasn't very adaptable. What came next?
So then we had statistical NLP, which was more data-driven. It used probabilistic models like hidden Markov models, HMMs, and conditional random fields, CRFs. These were used for tasks like part-of-speech tagging, figuring out if a word is a noun or a verb, and named entity recognition, which is identifying things like names of people, organizations, or locations in text.
So it was more about finding statistical patterns in language data rather than relying on hard-coded rules.
Exactly. And as neural networks continue to advance, people started using RNNs and then LSTMs, those long short-term memory networks we talked about earlier, for NLP tasks like language translation and text generation. But like we discussed, those models still had some limitations, especially with those pesky long-term dependencies in text. And they weren't very efficient at using parallel computing, which meant training could be really slow.
Right. And how about the way computers were representing the meaning of words? That seems pretty fundamental to language understanding.
Oh yeah, that's crucial. Techniques like word-to-vec and glove were a big deal back then. They were all about representing words as vectors, basically lists of numbers, that captured their meanings and relationships to other words. So the idea was that words with similar meanings would have similar vector representations. This helped computers understand that words like king and queen are more closely related than, say, king and bicycle.
So it's like mapping words onto a kind of meaning map.
Yeah, exactly. But there was a key limitation. Each word had just one static representation, no matter how it was used in a sentence. So think of the word bank. It could mean a financial institution or the edge of a river. But word-to-vec and glove would give it the same vector in both cases.
Mhm.
That obviously created problems because context is so important for figuring out the true meaning of a word.
Right. So AI was still missing that deep contextual awareness when it came to language. Okay, let's shift gears now and talk about the infrastructure side of things. How were businesses building their software applications before 2020 to support all these AI efforts?
Well, when it came to software architecture, monolithic architectures were pretty common. You can picture it as a single huge application where everything is tightly integrated. It's like building a giant machine where all the parts are inseparable.
And what were the downsides of that approach?
It made things really tricky when it came to scaling, making changes, or adopting new technologies.
Yeah.
Everything was so interconnected that if you wanted to update one part, it could often break something else. It was like trying to renovate a house without being able to turn off the electricity or the water.
Oh, so one small change could potentially bring down the whole system?
Pretty much, yeah.
Yeah.
And of course, we had client-server models, which were common for distributed applications. But, people were also starting to adopt service-oriented architecture, or SOA. This tried to break things down into more manageable chunks with loosely coupled services that could communicate with each other.
So it was a step towards more modularity.
Exactly. And of course, cloud computing was becoming more popular for deploying and managing applications. It offered all sorts of benefits like easier access, cost effectiveness, and the ability to scale resources up or down as needed.
So the seeds of modern cloud-based architectures were being sown, but was everyone using it? Not really. The idea of microservices architecture, where you break down applications into even smaller, independent services, that was being discussed, but widespread adoption didn't really happen until after 2020. So, the foundations were there, but a lot of organizations were still working with these older, more monolithic setups.
Got it. So the stage was set for some major changes. And that brings us to what many consider a pivotal moment in AI history, the arrival of the Transformer Network in 2017. What was it all about, and why was it such a game changer?
The Transformer Network was a real turning point, especially for dealing with sequential data. It introduced this revolutionary concept called the self-attention mechanism. This allowed the model to consider all the words in a sequence simultaneously when processing any individual word, assessing how important each word was in relation to all the others.
So instead of going through a sentence word by word, it could look at the whole thing at once and see how the words all fit together. Exactly. And that meant it could capture both short-range and long-range dependencies between words much more effectively than those RNNs we talked about. Those RNNs that had that short attention span. Transformers could remember information from much earlier in the sequence, which was crucial for really understanding context and meaning.
So it solved that long-term dependency problem that was plaguing earlier models.
It really did. And on top of that, transformers were designed to process information in parallel. This made them significantly faster for both training and inference, especially when dealing with massive data sets. They could crunch through data much more efficiently than those older models.
Okay, so it was a real leap forward in terms of efficiency and understanding context. What kind of impact did this have on NLP specifically?
Oh, the impact was huge. It revolutionized the field. The
Yeah.
transformer basically became the architecture for state-of-the-art NLP models. And this superior ability to handle long-range dependencies and its parallel processing capability, they led to breakthroughs across a whole range of NLP tasks, like take machine translation, for example.
Right, translating languages.
Exactly. Transformers could maintain context over much longer segments of text, which made translations much more fluent and accurate. Like it could actually understand the nuances of an entire paragraph, not just individual sentences.
I see. So it could capture the overall meaning and flow of the text much better. What about other areas of NLP?
Yeah, so text summarization saw big improvements too. Imagine trying to summarize a long research paper, right? Transformers could understand the whole document and generate really coherent and informative summaries rather than just pulling out random sentences. And question answering systems, they got much better at understanding the relationship between a question and the relevant information so they could provide more accurate answers. Even sentiment analysis, which is trying to gauge the emotional tone of text, that benefited from this enhanced contextual understanding. Like it could pick up on sarcasm and subtle cues that earlier models would have missed.
So it was really a paradigm shift in how we were approaching NLP. And then building on the success of the Transformer, we had BERT come along in 2018. What was BERT all about?
BERT, which stands for bidirectional encoder representations from transformers, kind of mouthful, but really pushed the boundaries of how deeply a model could understand the context of words in a sentence. Its key innovation was bidirectional training. So unlike those earlier models that looked at text in a single direction, like left to right, BERT was trained to consider both the left and right context of each word.
Oh, so it was like looking at a word and understanding both what came before it and what came after it all at the same time.
Exactly. And that allowed it to grasp the meaning of a word in a much more complete way. It was no longer just relying on one side of the context.
Okay, so it had a much more holistic view of language. How did they actually achieve that bidirectional training?
They used a couple of really clever pre-training tasks. The first one was the masked language model, or MLM. It's kind of like a game where they'd randomly mask some words in a sentence, and BERT had to predict what those masked words were based on the surrounding context.
Oh, so it was like filling in the blanks in a sentence.
Yeah, exactly. And that forced it to really learn the relationships between words and understand the meaning of a sentence as a whole. The other task was next sentence prediction, or NSP. It was all about figuring out if two sentences actually belong together, if they followed each other logically.
Yeah.
But to be honest, the effectiveness of NSP has been debated a bit since then.
Interesting. So MLM was the real star of the show. Okay, so BERT had this much richer understanding of context. How did that compare to those earlier word embedding techniques like word2vec and glove?
Well, it was a huge leap forward. Remember how those older techniques produced static word embeddings? Each word got the same vector representation no matter what. But BERT was different. It generated contextualized word embeddings. So the vector for a word would actually change depending on the other words in the sentence.
So it could finally understand that bank in one sentence might mean a financial institution, while in another sentence it might refer to a riverbank.
Exactly. That ability to handle polysemy, those multiple meanings of words, it was a game changer. And another cool thing BERT did was to use subword tokenization. So it would break down words into smaller, meaningful units. This allowed it to handle words it had never seen before by representing them as combinations of those known subword tokens. It was like having a language decoder ring that could decipher even the most unfamiliar words.
Makes sense. So BERT was much more flexible and adaptable than those earlier methods. Okay, with this improved contextual understanding, what new doors did that open for businesses? What kind of applications were made possible?
Oh, the possibilities were really exciting. It really had a huge impact on how businesses could use AI.
Yes.
Search engine results became a lot more relevant because those engines could finally understand the intent and context behind a user's query. They weren't just matching keywords anymore. They could actually figure out what the user was really looking for.
So it was like they became mind readers.
Kind of, yeah. And
Yeah.
sentiment analysis, understanding the emotions expressed in text, that became much more accurate too. BERT could pick up on sarcasm and subtle cues that those older models would have missed. It could really understand the nuance of human language.
Okay, and what about other applications?
Yeah, so uh, question answering systems became much more effective. Spam detection got better. Categorizing documents by topic, classifying news articles, all those things improved significantly because BERT could understand the content so much better. And we also saw advancements in information extraction, which is automatically pulling out specific pieces of information from text, like identifying names of people, organizations, and locations. That became much more accurate thanks to BERT's ability to understand context and relationships between words.
So it really had a broad impact. And architecturally, how did BERT change things? Did it influence the way these systems were built?
Absolutely. Architecturally, BERT, being based on that transformer encoder, it became this foundational piece for a lot of later models. But maybe the biggest impact was the widespread adoption of the pre-train and fine-tune paradigm. It was like this two-step process. First, you train a big model like BERT on a massive amount of unlabeled data, just tons of text, to give it a really good general understanding of language.
Kind of like giving it a crash course in human language.
Yeah, exactly. And then once it had this strong base, you could fine-tune it on a much smaller, more specific data set for a particular task. So, for example, you could take a BERT model that had already learned the basics of language and then fine-tune it on a data set of customer reviews to make it really good at understanding sentiment.
So it was like having a highly trained, multi-purpose language expert that you could then specialize for a specific job.
Yeah, that's a good way to put it.
Yeah.
And this pre-train and fine-tune approach had some huge advantages. It drastically reduced the amount of labeled data you needed for specific applications, and it made development much faster because you didn't have to train a model from scratch every time.
So it was a win-win for accuracy and efficiency. What were the main benefits for businesses adopting this approach?
Well, first of all, you had more reliable and effective AI applications. The increased accuracy and language understanding meant those applications could actually do their jobs better. And because of this reduced need for manual feature engineering and all that tedious handcrafting of features, businesses could save a ton of time and resources. Plus, development cycles became much faster thanks to transfer learning.
So it was like AI was finally starting to deliver on its promise.
Yeah, exactly. And ultimately, businesses could provide much better customer experiences. Things like smarter chatbots, more intuitive search functions, and truly personalized recommendations, those all became possible thanks to BERT and this new way of doing things.
Okay, so BERT gave us a much deeper understanding of language. Now let's move on to GPT and the rise of large language models, or LLMs. What made GPT such a breakthrough?
GPT stands for Generative Pre-trained Transformer, and it really marked a big shift in AI's ability to generate human-like text. Unlike earlier methods, which often relied on simpler statistical techniques or rule-based systems, GPT leveraged the power of that transformer architecture to learn language patterns from just tons and tons of text data, and it did it in a really sophisticated way.
So it wasn't just about understanding text, it was about AI actually creating new text that sounded like it was written by a human.
Right, and we saw the evolution from GPT-1 to GPT-3, each generation getting more and more powerful with more parameters and trained on even bigger data sets. GPT-3 in particular was really impressive. It could generate text that was often indistinguishable from human writing, like you could give it a prompt, like write a poem about a cat, and it would actually produce something that sounded pretty darn good.
That's amazing. So how were they designed architecturally?
Well, these GPT models usually use a decoder-only transformer architecture. This means they're really good at what we call autoregressive language generation. It's like predicting the next word in a sequence based on the words that came before. So it's like a really smart autocomplete, constantly predicting what word should come next based on the context it's built up.
Okay, I think I get it. So GPT was a big leap in terms of text generation. And then things evolved even further into these large language models, right? What makes LLM special?
Yeah, LLMs are essentially GPT on steroids. They're these massive models, often with billions or even trillions of parameters, that can do so much more than just generate text. They can translate languages with incredible accuracy, answer really complex questions, and even write computer code. It's pretty mind-blowing what they can do.
So they're like the ultimate language whizzes.
Pretty much. And a big part of their success comes from the way they're adapted to specific tasks. Fine-tuning them on particular data sets is still a common technique. But then there's prompt engineering, which has become really important. It's all about crafting very specific prompts to guide the model's output. Like instead of just saying, translate this text, you might give it a prompt like, translate this text in a formal academic style. and that would influence the kind of translation it produces.
So it's about giving the model clear instructions and context to shape its output.
Exactly. And this led to the idea of foundation models, with models like GPT serving as this versatile base that can be adapted for all sorts of applications across different fields. They're like those Swiss Army knives of language models with all these different tools built in.
Okay, with all this power, what new possibilities did this open up for businesses? What kind of applications did GPT and LLMs enable?
Well, all sorts of things, really. Like you can now have chatbots and virtual assistants that can engage in really natural, human-like conversations. This can completely transform customer support, providing a much better user experience.
So no more of those frustrating chatbot interactions where it feels like you're talking to a brick wall.
Yeah, hopefully not. And then there's automated content creation. Imagine being able to generate high-quality marketing copy, articles, blog posts, even technical documentation, all automatically. That can save businesses a ton of time and resources.
It sounds like the potential for increased efficiency is huge. What about other applications?
Oh yeah, language translation services got even better, becoming more accurate and fluent thanks to LLMs, and developers are now using them to help write code, which can really boost productivity. And then there's the ability to summarize those really long, complex documents. It's like having a super efficient research assistant that can condense all that information down to the key points.
Okay, so lots of exciting applications. Architecturally, what changed with GPT and LLMs?
The decoder-only transformer architecture became the standard for generative tasks. And that pre-trained and fine-tuned paradigm that was still really crucial for adapting these massive models to specific use cases. And, like we talked about, prompt engineering became a really essential skill for controlling the behavior of these models.
Right, it was like learning how to speak their language to get them to do what you wanted. What are the key takeaways for businesses? Why should they care about all this?
Oh, it's all about efficiency, right? LLMs can automate all sorts of text-based tasks, saving time and money. Plus, you get better customer engagement because you can provide these sophisticated human-like interactions, and new features and products can get to market much faster because you don't have to build everything from scratch.
So it's about staying ahead of the curve in a world that's increasingly driven by AI.
Absolutely. All right, so we've seen AI evolve from understanding language to generating it. Now let's talk about AI that can go beyond text and understand other types of data. Multimodal models. What's the big idea behind those?
Yeah, multimodal models are really cool. They're designed to handle information from multiple sources, not just text. So things like images, audio, video, they can process all of that and understand how it all fits together. It's kind of like how we humans experience the world, right? We don't just rely on one sense. We use sight, sound, touch, all of it together.
So it's like giving AI a more human-like perception of the world.
Exactly. And it opens up so many possibilities. Like, imagine a system that can look at an image and read a caption and understand how those two pieces of information relate to each other. Or a system that can answer questions about a video by analyzing both the visuals and the audio. That's the power of multimodal AI.
Okay, I'm starting to see why this is such a big deal. How does it compare to what we were doing before? Well, before 2020, AI was mostly unimodal. It could only handle one type of data at a time. So it was like trying to understand a story by only reading every other page, or listening to a song with one ear plugged. You're missing a lot of the context.
Right, you're only getting part of the picture. So multimodal models fill in those gaps by combining different data sources.
Exactly. They can integrate all that information to get a much more complete understanding. Like, think about those customer reviews we talked about earlier. A traditional sentiment analysis model might just look at the text of the review and miss some crucial context. But a multimodal model could also analyze any images the customer uploaded, along with data about how they interacted with the product online. All of that can provide valuable insights into their overall experience.
So it's about getting the full story, not just a snippet. What kind of new applications has this enabled?
Oh, there are so many possibilities. It's already having a big impact in areas like autonomous driving, where you need to combine data from cameras, LiDAR, and radar to get a full picture of the environment.
Right, it's about making self-driving cars safer by giving them a more complete understanding of their surroundings.
Yeah, exactly. And in finance, it can help with risk management and fraud detection by combining all sorts of data, like transactions, account activity, communication records, and so on. It's like connecting the dots to spot patterns that you might miss if you were just looking at one piece of data in isolation.
Makes sense. What about other areas?
E-commerce is another big one. You can personalize recommendations and marketing much better by combining product images, user reviews, and browsing behavior data. In education, you can create more engaging and personalized learning experiences by seamlessly integrating text, video, and interactive content. And in healthcare, it can help with medical diagnosis by combining medical images with patient records, lab results, even genetic data. The possibilities are really endless.
Wow, it sounds like multimodal AI is revolutionizing a lot of industries. So, how are these systems typically built? What's the architecture like?
Well, you usually start with separate encoders for each input modality, often using those powerful transformer networks we talked about, or convolutional neural networks, which are good at image processing. Each encoder converts the raw data into a form that the model can understand.
So, it's like having specialized translators for each type of data.
Yeah, kind of. And then you have this fusion mechanism that takes the output from those encoders and combines it into a single unified representation. There are different techniques for doing this, like attention mechanisms, which can learn which parts of the data are most important to focus on, or simply concatenating the features, which is just sticking them all together in a big list.
Okay, so it's about finding clever ways to integrate all that information. And what are the main benefits for businesses that embrace this approach?
Well, the biggest one is that it just improves performance and accuracy across a wide range of tasks. You're getting a much deeper, more nuanced understanding of whatever you're analyzing, which leads to better insights and predictions. Plus, you can create more natural and intuitive interactions between AI systems and users.
Right, it's about making AI less robotic and more human-like in its interactions. Okay, so we've talked about how AI is getting much better at understanding and generating different types of data, but what about accessing and using external knowledge? How does that work?
That's where Retrieval-Augmented Generation, or RA, comes in. It's a really clever way to enhance those large language models by giving them access to external knowledge sources, like big databases of documents or even the entire internet.
So it's like giving them a super-powered search engine that they can use to find information they need.
Exactly. It's a two-step process. First, the system retrieves relevant context based on the user's query, and then it uses that retrieved information to generate a more informed and accurate response.
Okay, so it's not just relying on its internal knowledge. It can actually go out and find new information to answer questions or generate text. What are the advantages of that?
Well, first of all, it means the model can provide answers based on the most up-to-date information. It's not limited to what it learned during training, which might be outdated, and it can also improve the factual accuracy of its responses because it can verify its answers against external sources.
So it's less likely to make stuff up or hallucinate, as they call it.
Exactly.
Yeah.
And it's also really good at integrating knowledge from different sources. It can pull information from all sorts of places and combine it into a coherent response.
Okay, so it's a big step forward in terms of accuracy and reliability. How does this compare to how things were done before?
Well, before R, if you wanted to update a language model's knowledge, you basically had to retrain the whole thing, which was a huge hassle and really expensive. Or you had to rely on static knowledge that was built into the model during training, which could quickly become outdated. But ROG offers a much more dynamic and efficient approach.
So it's about making those models more adaptable and keeping them up to date without having to go through that whole retraining process.
Exactly. And a key technology here is vector databases. They allow for really efficient retrieval of documents based on their semantic similarity. So both the user's query and the documents in their knowledge base are converted into vector representations, those numerical representations of meaning we discussed earlier. And the vector database can quickly find the most relevant information.
So it's not just matching keywords, it's actually understanding the meaning of the query and the documents to find the best match.
Exactly. And all of this has opened up a bunch of new possibilities for businesses, like customer service chatbots can now access all sorts of up-to-date information, like product specs, company policies, even customer account details, to provide more accurate and helpful responses.
It sounds like a dream come true for customer service agents who are tired of answering the same questions over and over again.
Yeah, for sure. And knowledge management systems can become much more effective, giving employees quick access to relevant information and expertise within the company. Researchers can speed up their work by instantly finding the most relevant scientific literature. E-commerce platforms can provide much better product recommendations based on real-time data. And financial analysts can integrate up-to-the-minute market data into their analyses. It's really revolutionizing a lot of different fields.
Okay, so RAG is about making AI more intelligent, but also more reliably informed. Now let's move on to an area that's getting a lot of buzz these days, generative AI or Gen AI. What exactly is that?
Gen AI is all about expanding the scope of what AI can do. It's not just about understanding and generating text. It's about creating entirely new forms of content in all sorts of different modalities. Like we have these amazing tools now like DALL-E, Midjourney, and Stable Diffusion
Hmm.
that can generate images from text prompts. They're powered by some really cool technology like diffusion models and generative adversarial networks or GANs.
So you can literally type in a description of what you want to see, and these tools will create an image for you.
Exactly. And they can generate all sorts of things from photorealistic images to abstract art to completely fantastical creations. It's really remarkable. And Gen AI goes beyond images too. There are models for generating audio, video, and even computer code.
So it's about AI becoming a creator, not just an analyzer or interpreter.
Yeah, that's the big shift. Pre-2020, AI was mostly focused on analyzing existing data, making predictions, classifying things. But Gen AI is about creating something totally new, something that didn't exist before. And it's all thanks to those advancements in deep learning, like transformers and diffusion models, and the fact that we now have access to these massive data sets to train these models on.
Okay, so it's a fundamental change in how we're thinking about AI and what it can do. What are some of the most exciting business applications for Gen AI?
Oh, tons of things. Like in marketing and advertising, you can use it to generate all sorts of content, ad copy, social media posts, personalized marketing materials. It can really speed up the creative process and help businesses come up with fresh ideas.
So it's like having an army of creative assistants at your fingertips.
Exactly. And it's also transforming the world of digital art and music creation, giving artists new tools to express themselves. And it can be used to create synthetic data, which is really valuable for training other machine learning models, especially when real-world data is scarce or sensitive. Like, if you're developing a medical AI system, you might not have access to a lot of patient data, but you could use Gen AI to create synthetic data that mimics real patient data, which can help you train your model without compromising anyone's privacy.
So it can help overcome those data limitations that we often face in AI development. What about other applications?
Yeah, so Gen AI is also being used for rapid prototyping and design. Like if you're developing a new product, you can use it to generate all sorts of different designs and explore a wider range of options much faster than you could with traditional methods. And it can help create those super personalized customer experiences, like tailor-made product recommendations and custom-generated messages. It's really about making.